special shout out to our patent attorney, Bob Lamberts. Can you raise your hand? There you go. Okay, over there. Our patent attorney from Latham & Gage. And to JEI staff, the people that have put a lot of hours in to develop a new system to be able to attach onto steel structures. And I also wanted to call out a special thank you, a shout out to KC Structural Steel, to Tim Olaf, president of KC Structural Steel. Is he here tonight, Mike?
He's not here.
He's not here? Okay. Mike Bennett here. Mike Bennett.
This way.
Oh, Mike over there. Mike Bennett with KC Structural Steel, vice president. And so a special shout out to everybody at KC Structural Steel. Whenever I was thinking about this, in my mind it was a concept, and we called up Tim Olaf, the president of KC Structural Steel, and we sat down together and we had 3D prints of this concept and a patent on it. And Tim Olaf, he looked at the first one, which was a little bit of a different idea. And then I gave him the second one. I was holding back on the second 3D part. And I gave it to him. I said, this one, this is going to be hard. This is a tough one to be able to do because it's actually an industry changer. It's a disruptor. And he said, he looked at it, he was just silent. He was silent, just looking at it for the longest time. And he held on to that concept, he held on to the 3D part so adamant, and he has brought it into an actual product. And so, hats off to you guys at KC Structural Steel. You guys are really awesome. Thank you, Dave. Dave, for putting this together and all BEC. Thank you very much. We're going to be discussing some of the traditional facade connections that we've seen out there for 70 years plus to structural steel. We're going to take a look at a new system that's going to change how we attach onto structural steel buildings. We're going to take a look at some of the advantages associated with that. It's called J-Edge Anchor, and we're going to also look at the testing information that's behind it, and also some of the engineering and load tables that have been developed to support it. So let's start by just taking a look at some of the typical facade details that we would see out there in the industry that have been around for a while and are still being used today. So this is masonry facade. It's supported by a typical linear ledge angle that is usually welded on, attached onto the steel frame up here. And it's usually field welded to this bent plate core stop. And so we're going to be talking a lot about that typical bent plate core stop. Some of the limitations that are associated with this is the field welding. The labor time and the cost are extreme on field welding. And so that's some of the stuff that we're looking at. Here's a different detail with the masonry facade where it's lowered down a little bit to avoid that steel core stop attaching to it. The problems with this is it still involves a lot of field welding. Every once in a while we'll see a bolted detail where they'll have a knurled insert that sits behind it. But they also have to build this plate out on the steel beam to be able to support the eccentric dead load associated with that. And usually they'll have to provide some sort of a lateral beam brace because there's rotation that's placed from that ledge angle. So let's talk a little bit about precast. This is some of the details that we see common in the precast industry where they'll have a special embed angle that sits up on top of the slab. And usually that has a lot of difficulties associated with the depth of the slab. We can see here that there's an eccentricity of where the load, the wind load, is actually being applied and where the load actually needs to go down to the top of steel. Because the load in structural engineering, we're always trying to get it down to the structural steel and into brace systems or moment frame systems. So that's where it needs to wind up at. The problem with that is whenever you have a certain amount of eccentricity for it, you pay for it. It's a moment that is trying to be resolved, and so the way that gets resolved is by this special embed that they have to put in there, and the reinforcing to reinforce that edge. You notice that they avoid the steel bent plate pour stop altogether in the attachment to this. So limitations are that it requires special setback. You lose real estate associated with it because of that connection. Here's a steel stud setup. A common detail that we see in the industry is a steel clip that attaches onto the studs. And the usual way that these are attached onto the steel frame is to the bent plate pour stop again. And the way it gets attached to the bent plate pour stop is either through a power actuated fastener system and or welding associated with that. Either way it goes, there's an eccentricity that is associated with the distance again from where the load is applied to where the load needs to go into the top of the steel. And so it's paid for in this bent plate pour stop. It requires a certain thickness in that pour stop to be able to transfer the loads through bending. Another one of the limitations is those power type pin fasteners. There are some questions too about the longevity of that during repeated cycles of the wind. So you might get 1,000 wind cycles per day, pushing, pulling on that system. And if these do not go through to the back of the system, there's questions about that. What prevents it from going through to the back of the system? Concrete. And so there's questions about the longevity of those types of fastener systems. So curtain wall systems, the typical connections that we would see in the industry start with one that is less common where it's welded on. We have welded clips. These are clip angles, and they attach, they weld these onto the bottom of the beam or part of the beam. The problem with that is it's extensive field welding that needs to occur. And there's 2 clips per mullion. And one of the additional difficulties associated with this detail is if you get this clip down low enough, it also provides a force to the bottom of the beam where it wants to twist it out of plane. So you would probably have some lateral bracing that's associated with that type of a clip welded onto the steel structure. More often than not, this is the detail that we see. So 95% of the time, this is the detail that happens with curtain wall construction where we have that same steel angle that's attached up, welded onto this steel bent plate. So that steel bent plate has to be sized for that eccentricity, that bending from that eccentricity. So the limitations for this type of connection are the high labor costs associated with the welding and all the time that it takes out in the field to be able to get this type of connection done. Every once in a while, we see a detail that is similar to this where we have an embed channel anchor that is cut inside of the pour stop and welded to the bent plate pour stop. The problem with this is, and the reason why it's so rare, is it's very, very, very expensive to do this way. It's got a lot of welding. The channel anchors are very difficult to get to work out, especially in a limited amount of distance with lightweight concrete. So these are very difficult to get to work out, and they're rare. You don't see them very often. The picture over here is that connection over there is a side anchor channel. Over here we have a top embed channel. And so this actually is probably on a deeper system where we have the bent plate. You can kind of see that out there. And that's the pour stop. And this embed anchor is framed out in a box, and it has rebar that goes underneath it that's welded off to it. And it has anchors that extend down underneath. Very, very, very expensive to be able to do that type of connection and weld it in place and get it into the field. Looking back, I've got access to some of the old buildings in Kansas City. This is actually a detail out of the Flash Cube structure where they're renovating that structure and replacing some glass. This is the detail that was used in the 1970s. They had that same steel edge bent plate pour stop. In this case, they're welding to the underside of it, field welds again, with a clip angle system to support the curtain wall that's on the outside. And so whenever they weld that in, there's not as much eccentricity, but there's still some, and they have to develop that back up into the concrete with an embed plate. And so this embed anchor goes in, it transfers load up into the concrete, and somehow that load gets transferred out back into the steel structure. Here's another 1970s building. This is the Kansas City Hall, where we did some renovation. And this is a precast detail. You can kind of see that there's that same bent edge steel pour stop. And they've got this curtain wall or this precast connection that is into the top of that where they have to field weld again. And so to get the loads in eccentricity, they have to transfer it through another embed anchor into the slab, and finally it gets into the steel structure, into the top of the steel structure. So we've been actually dealing with this same bed plate pour stop for 70 plus years. We've been working around the issue. Yeah, you're thinking 1970, not quite, but it goes farther back than that. It goes another 20. This is only the examples from Kansas City. So, yeah, I saw that. But this is the same detail that we've been working with for a very long time. Trying to get the loads through that steel bent plate or around that steel bent plate and somehow into the steel structure. And so we're going to be talking about that. That is a problem whenever we have eccentric loads that are loading into that. So introducing J-edge anchor. This is a new concept that is going to change the way that we're attaching onto steel building. It's a continuous pour stop, and it's a continuous anchor system around the edge of your building. And so one of the things that I want to introduce to you right now, go ahead, JEI guys, get those samples and start passing those around to the people when they're sitting down. So it's a real product. It's actually out there right now. There's a certain amount of extruded part, and it is a welded system directly to the top of the steel structure system. So let's talk a little bit about some of the advantages to this new concept of being able to handle the loads in a better way. Here's one of the major advantages associated with it. So this is the old bent plate pour stop. We're taking a load in an eccentric manner. It's got a distance between where we're taking the load and then getting the load into the top. Causes bending in this bent plate. And this is a concentric reaction. So where it lines up exactly with the top of steel. We're taking the eccentricity out of the system. And that equals a better load path and more capacity to your anchor system. So the better load path, whenever we have that eccentricity that's up on the edge of a bent plate, it starts to bend it right around the bend line. That's where the stress is in your bent plate. That's the reason why this has a better capacity for allowing that load to get into the steel structure. We're going to talk a little bit more about the better load path and how much capacity that is better, how much more that we can get out of the J-edge anchor. But look at this. Here's the second heading down. It's got stronger steel. The J-edge anchor system, because it's an extruded part, it has 60 plus KSI yield strength. And so we got mill surge, we're getting those in. And so it's ending up there way above the 36 KSI yield strength for a standard bend plate. And so we get an increase of over 60% just based off of the better steel that is being used in this J-edge anchor system. Now let's talk a little bit about the better load path and how much increase in capacity does that give us. So just running a standard load that we would see on a typical curtain wall clip of 400 pounds dead load with a 1,000-pound wind load. This is per clip, so there's 2 clips per mullion. This is kind of a standard load that we would see. If we applied that onto a bent plate pour stop, and it's a 6-inch deep slab, and this is at the center of that 6-inch deep slab. This is the maximum moment that you come up with for that load, those loads associated with the standard load. 6,341 pound-inch. That represents a bending load on that steel pour stop. The same load produces 2,392 pound-inches. The difference between these two represents the increase in capacity that our standard edge anchor has, which is over 150% increase in the capacity just because it's got a better load path to get into the steel structure. Those two things combined, the better steel and the better load path, combine for an increased capacity of over 200% for the J-edge anchor in being able to handle loads and get it back into the building. So let's take a look at some of the other advantages that we see associated with this anchor system. Obviously, one of them is it's an adjustable bolted connection. So this avoids the costly field welding that's associated with the bent plate pour stop. So they're running around, their field labor associated with each one of those is being saved. And so there's equipment, there's lifts, there's inspection, there's safety, all kinds of stuff associated with the field welding that is saved. And this is a bolted, easy connection. It saves times and reduces mistakes for anchor installation. So you get this thing off in the wrong spot, what happens? Well, they have to cut it off, and they got to redo it. And so it saves the costly mistakes as well. Here's the key benefit, though, that I want you to really lock into. And I've capped it, and I put it all in caps. It reduces construction schedule. The overall install time, whenever you think about one of these clips, it's a clip angle that's going to hold the mullion in place. And so we've got a mullion that sits in here, another clip on the side. Think about the welder whenever they're going out into the field. They've got to get on the lift, they've got to position the lift, they've got to raise up the lift, they've got to position this just right. It's got to be exact, because if it's off, you're messed up. So they make sure it's all right, then they weld. They weld across the top, they weld down the side, maybe partway down the side, and every once in a while, they have to weld along the bottom edge if there's enough load in the system that needs to be taken into that bent plate pour stop. After that, they've got to do the next one and weld in on it. Then they lower the lift, reposition the lift over to the next mullion, do it all over again. A lot of time is built into that process. This is a time that has been used by some of our glazing contractors as an estimate in their estimates. 15 minutes a clip. That time, and also the time to laser map and plan out everything exactly, some of that time can be saved off of the construction schedule, and going with a bolted system where it's easy to adjust and get that eliminates a lot of that cost associated with it. And it reduces the construction schedule. One of the additional features of this system is it's an extruded part. So it's very straight. We get complaints all the time. I ask glazing contractors, how much effort is there, to adjust for tolerances? And I said, is the bent plate around the edge of the building, is it straight, or do you have a lot of adjustment? He said, you believe it, Stewart? It wobbles in and out, plane all over the place. I mean, there's a lot of adjustment that they have to make with that. This is a straight extruded edge to your building. So tolerances eliminates a lot of the tolerance issue associated with the welded connections. Here's another example of a possible advantage. And so there's a little bit of history associated with this advantage that I want to kind of talk about a little bit beforehand. We can kind of see that with a bent plate pour stop system that is typical, the only way to have safety railing for your construction workers is to have this welded angle post and then run cables from post to post. Now, there are some other systems out there where they use some wood, stuff like that. But for the most part, this is done. They just weld inside to this steel bent plate. And so we can kind of see that in this picture up here. We see the bent plate steel forestop, and that is welded to the inside of that bent plate forestop. So what happens whenever they get done with construction? What happens when the concrete's in there? What do they do with it? They cut it off and leave it there. So part of that's actually in the concrete. It creates a point for that curing concrete to actually crack. That's left in place. All that safety drilling goes to waste. It goes to scrap. This is one of the things that's being developed by KC Structural Steel. They're in the process of testing this. This is a reusable safety construction railing which has an adapter that bolts right into the J-edge anchor system. Quick and easy to use, reusable for your next job site. Saving cost and time. Another concept that KC Structural Steel is working on right now is ease of temporary enclosure. Using that same adapter that bolts into the J-edge anchor system, they're able to run posts floor to floor and actually put a temporary barrier on and close this off very quickly. One of the other additional items might be a thermal brake that is additional to your thermal brakes in the curtain wall to prevent thermal loads from your curtain wall system traveling through the welded steel anchor system. So it creates an additional possibility of a thermal brake, the same thermal brake that is used right now in structural connections of beams that need to have thermal brakes. Now here's an interesting one that I want you to think about a little bit. If we have a cassette system that's a curtain wall system that has a toggle that actually attaches the glass in place, the glass actually becomes somewhat replaceable. Whenever you combine a cassette system with a toggle where you can replace glass with the J-edge anchor system where you can actually adjust the curtain wall framing members, what does that do for reuse possibilities in the future, say 10 years later? Maybe you have something like this that you can easily retrofit into something like that with some adjustments, replacing of the glass. KC Structural Steel has options already developed and they're being used right now for this type of an extension where we have beams that are set back from the edge of slab. The extended angle system, and it's the same system that's being used on bent plate forceps right now. We just have bent plate forceps there, and so instead of that, we have the J-edge anchor system, and there's also options for extending the J-edge anchor system for any depth of concrete that you need to have in your project, and also options for being able to have the welded rebar option to develop the loads back into the slab. Is that needed? That's a good question. Is that needed anymore now that we have all of the loads going into our system right here in a concentric manner? We now don't have any bending up here in the top region of the slab. This may not be required unless there's some contractor that wants to weld off to something in the future. But with the bolted system, I can't see a reason why they would. So what does it look like? We talked a little bit about curtain wall and what it looks like for curtain wall. What does it look like for some of the other facade systems that we see in those previous details that we talked about? So we talked about this detail that had the embedded stud and the anchor for the precast and how it was eccentric and you had to reinforce around that area and push the real estate back and you had less real estate because the studs had to make way for that connection. So this is a possibility where we have a braced anchor system up to the top. But this is, and we save the real estate, we save the embed stud into the top of the slab and the reinforcing and all the other stuff. But this is probably better. where we attach to the bottom side, and we just take it in a simple plate connection and transfer the loads directly into the top of the beam. What about masonry? Well, we talked about that ledge angle that was continuous, where we had to weld it on, field weld it on to the bend plate pour stop. You had to have the reinforcing that developed the loads because it's got an eccentric load on it. It's bending that plate outward. Now we have a bolted system, which takes the loads back into the top of the steel beam. What about the cold-formed steel? Lightweight cold-formed steel, where we have cold-formed steel that runs by the exterior of the building. We looked at that detail where we have the bend plate pour stop, and it brings loads in an eccentric manner. It bends that plate, so we pay for it in the sizing of the plate. We also have the power-driven fasteners that may have some questions about longevity because of cyclical winds. Now we have the options for a bolted clip instead of that, and or some possible fasteners because we have open air. We can now attach into open air areas if we wanted to have those direct positive fastening systems with cold-formed steel. Cost. Everybody's been thinking about cost, I'm sure. The actual cost is better than a typical bend plate pour stop. Here's the reason why. The increased cost of the part, especially for now because it's not in bulk yet, is less than the deducts that we see for this construction. Here's a real example from KC Structural Steel, medium-sized office building, about 7 floors. The cost increase for this extruded part versus bent plate, standard bent plate, about $92,000. The deduct that we get for all of the welding, where that guy is going around the edge of the building, welding each clip, anchor on, and the safety, the lifts, all that stuff associated with it, $200,000 deduct equals a savings, an economic savings in the overall cost of the building. Now this doesn't include savings for reusable safety railings, the faster construction schedule, the value, the economic value, possibility of being able to open your office building 3 weeks earlier because you're able to enclose the building that much faster. So this really has some advantages over the typical bend plate pour stop, economic and other advantages. So let's talk a little bit about the testing that has gone into this system. Has it been tested? Yes. KC Structural Steel has provided for a pre-test at KU Engineering Lab, focusing on tension and shear. Now this is a picture of a shear test where we loaded up a similar structure that we would see like 2 glazing clips out beside a mullion that sits in between. And we loaded that up as much as they could, and they ran it up to see what the ultimate load would be on it. Let's talk a little bit about the tension test. It's just where they pulled as much as they could all the way up to where the bolt failed, and it pulled out of the system. And those average loads that they got up to, about 28,000 pounds on average. What's our average curtain wall load for a single clip angle? About 1,000. We're well below the allowables and the yield and the ultimate for that. We're way down on this graph, way down there. Shear testing. That shear test that we saw in the picture, we have a dead load that sits out here, and we push that as much as we can. And so the average shear tests are popping up around 20,000 pounds. Not controlled by failure of the system. It's actually controlled by safety because they had to take the load off because the incidence between the rotation of the system and the applied load was becoming unsafe. So they got up to 20,000 pounds and they said, okay, we're going to take the load off there. But ultimately, we can see from the graphs and the charts that we've got a good linear progression in there that indicates that there's not a yield yet, up to about 12,000 pounds. Where is the average curtain wall dead load? About 400 pounds per clip. That's what we would see on average. So there's a huge difference. We're way down here in the allowable range for from all deadwoods.
Stewart, would you see failure in your bolt on shear as well, or where would you anticipate failure if it wasn't a safety concern? You test that failure, what would happen?
We couldn't get there, so.
Okay.
It might be bolt failure, it might be bolt shear that actually produces the ultimate demise of this.
Okay.
Let's back up and kind of look, that's a good question. You kind of look at this test and they're pushing, they actually mounted this thing upside down so that they could get a actuator in there and load it. And so it would actually twist this so much to where it would be way off and it became unsafe. So that's the reason why we didn't see bolt failure, being an issue associated with that prying action. So just a little bit about the engineering that has gone into this. Many, many, many hours. Finite element analysis associated with the engineering to put this onto the table just to get it out of the concept stage. And so this is a finite element analysis model that has only tension. It's got a real bolt and an anchor that it sits inside the channel that's modeled into it, and we apply tension onto it. And this other is the same exact assembly that we see in the vertical shear test, and it shows that we can handle a heck of a lot of load on this system. Ultimately, whenever we get the plots, all of it is under the yield stresses very easily. We've even done interaction load tables based off of the tested data associated with a safety factor applied to the tested data. And so we can see the interaction of the bolt with tension and shear on that bolt, where we should be at versus the tested data and the engineering. All that to say, there's a lot of benefits associated with this. There's a lot of testing data that we have associated with it. There's a lot of engineering to back it up. And for any project, we are confident that we can put the engineering data together and the calculations necessary to support the project. Summary. We covered the traditional facade limitations. We covered some of the advantages associated with the J-edge anchor system, the economic advantages associated with that as well. We covered the J-edge anchor testing information and the engineering and load tables that are behind that. We're going to get into questions, but at this time, I'd like to ask that Mike come up and he share the stage with me, and we're going to reserve all the hard questions for him.
No, I don't know about that.
So, the first question that I would have for you, if I was somebody in the audience, would be, how does somebody get this in their project?
Well, it all starts from doing the design. That's what we're here. We're trying to designer teams are really so we can get it into some projects. We've already got some leads on, I think we're close to selling on a good project. Park, Metcalf, 95th, historic building. So there's a lot of features already in this system. The sooner we get it in designers' hands and buy into the system, the better off.
What questions are there out there? Go ahead.
What do you think about the
Can you state your name
Jeff Peterson,
and who you're with?
DLR group?
Okay.
How about the cost analysis for brick ledge angles? We saw the one for curtain wall, but what would that be?
Yeah, see, we started this whole process behind the curtain wall system. So all these other ideas are starting to develop behind it, like the safety post system and everything like that. So cost analysis, we're still in development on some of that, but we will be using that shortly, and we'll put it on the website to show everybody.
Yeah.
Burn Keith, I want to follow up. Say that I want to ask a typical endpoint relative to the ID in the shop as it goes up. So this is the fabricated in the shop.
Most likely. So, I mean, this project I'm talking about in Illinois Park, they say it's their job. They're buying from us.
But it could be.
Because J&M is interested in time savings and everything else.
As far as cost savings, so you kind of want to be a little modest with that, because I see a lot of the construction steel side not having girls for electricity or braces, that cost coming out of
didn't really touch on was with this, like the safety post feature, that whole system is maybe 1.5 inches wide, and the post actually tapers back into the building about 10 degrees. That allows you to install your facade system without ever touching the safety post. And then you pull it out, and you don't install
Doug, you're at Argon. Explain to me again how extruded steel is stronger than a, I don't know, I suppose state steel, whatever the simple steel is.
For the bent plate?
Yeah, bent plate.
Well, it ends up being stronger the way we're doing this process. We've got all the mill certs in for this so far. We've told them minimum of 55 KSI and I think we're about 62 KSI right now.
Okay.
So, and the way the extrude process works is it's really amazing. I haven't think of more than people use it once, but it's basically a 10-inch round billet of steel. They turn white hot, just force it to a die, and comes out the other side about 22, 25 foot lengths.
Okay.
They call that electromagnetic induction or something?
Correct.
That was the term.
Correct.
Yeah.
Correct. And that's, like you said, there's about 60 PSI.
Is the alloy different in the steel from the billet as
Still
opposed
carbon
to?
steel,
Okay.
still the same alloy.
Okay.
Question?
Go back on your masonry.
Excuse me?
Sorry. Back to the masonry detail.
Go back to the next detail.
So can those be offset so that you're only connecting in 10-foot increments, or do they have to be a continuous connection?
So the question is, can they be offset so that you have it in 10-foot increments? In other words, can this piece be in 10-foot increments and then offset along the building so that you put in bent plate in between?
Well, so like for instance, now we put in, if we're trying to reduce the thermal bridging, we basically put in a tube and offset the steel angle, so
Oh.
it's not continuous against the slab edge.
Right?
And so here you got a direct connection, and I know you talked about that on the curtain wall, I wasn't sure.
Yeah.
Yeah, and it's funny you say that because something Stewart did mention, because we're way early on in this, but we are developing a thermal brake system to be used with the JH.
But yes, the answer is yes. It's going to be dependent on load. So we have to kind of run some calculations in the interaction tables that we have in the test data and find out where it's at. Good question. I meant to do something for the really good questions out here. I'm waiting for one, and I'm like, here you go. It's a $10,000 bar right now. It's a good question. Yeah.
Julia with Turner Intel. I'm gonna ask a question that I think here's some contractor asking me. So when your slab is taller than your J edge, they have to put more work up to make that work?
That's a good question. So when we sell this product, we are limited right now to the size we can get that top edge.
Yeah.
It's 4.5 or 5 inches. It's 5 inches. But we're using it on projects that are 7.5 inches. So in our shop, we produced an extension on the top of that. We will on an extension.
You will, okay.
We ship it out. So it'll be converted to whatever the depth of your slab is.
Another question caused me to go to a reserve slide. $10,000.
Go ahead, Ryan.
So one of you, see everything here right now is cladding. You look at anything larger, yeah, shading devices or any other industry. And the other is, Jeff, are you working on anything like this for concrete service?
So the question, if I understand it right, are we working on other systems beyond the cladding that we kind of indicated there? We are. And then the other one is, are we working on any concrete insert systems? We're not yet. We have some thoughts and some ideas associated with post-tension. And we're meeting up, I've got to meet up with some post-tension guys.
I think overall, it's developed as a curtain wall system, and since then, we've obviously bought many more uses for this that will continue to grow.
Other questions?
The fastening, John Hayward, Paragon, the fastening bolts that you have there, is that a proprietary design that can't be retrofitted or can't be made up in the field with various nuts and bolts and washers?
Now, they are specialty bolts. We have produced, we actually went through a few rounds of expensive rounds. The first ones didn't fit real well. So then we took it upon ourselves to, like they did, buy a 3D printer and actually buy, the orders. I have a few questions I brought here. We're in the third round of getting these going. As useful as they can. We're actually tapered on part of it so it actually sits itself in there as you do it. So the answer to your question is we produce the bolts.
Right.
And they come with the system.
Yeah, you are. Other questions?
So if it's decreasing the time, like during construction, how long is it increasing the additional fabrication type of thing?
I couldn't get that all the way, so say that again.
So like, you're decreasing the construction time, like during construction, but I would think it would take longer to fabricate this piece. So like, how long is it increasing that front roll and
So it's really a matter of manufacturing. So this piece isn't any more for like a steel fabricator to put on, a structural member, but to have, that piece is gonna be stocked. So we have a huge supply of this already in stock, and we'll continue to produce ahead of time, so there'll never be a shortage when the project comes up, so. But it's not gonna be more time to fabricate.
But order now.
And we're in the early stages, so all that's very good. It's steam right now. Yeah.
In the extrusion process, I'm familiar with aluminum extrusion, but do you have to temper this at all? Once it's out of the press
It's not
and
tempered.
it's done. Okay.
By the extrusion process itself.
I need to-
It actually goes through a template process.
Yes, it does. Yes. So I do have a video of the process, which is really cool. See, I might be able to carry it put up on the website.
Okay. To me, it's, I'm familiar with steel extrusions, that's kind of intriguing.
Oh, and back to the safety goes real quick. The extrusion for the safety goes to the front of the extrusion itself. And with the intent of purchasing the extrusion you use on our project.
Here's a question.
Javier with JI, could you just highlight the importance of making this decision very early on at the construction stage for the design team so that the savings and the full benefit of it are seen, are highlighted?
Yeah, so obviously the earlier that this is planned out in drawings, like getting the details in there, which are gonna be on the website shortly and into your projects, the better off people are for getting this planned out into their system.
So. I guess that's because I have one.
Yeah, Bob.
Stewart, Bob Lambrex, Lathrop. Periodically, I crack open the Business Journal and I see about the significant shortage of qualified or trained welders all across the country, and certainly here in Kansas City. And it seems like that would have a significant impact. I mean, you talked about that a little bit here in terms of if you can get away from needing really high-skilled welders, it seems like this would be even more of a motivation or incentive to utilize the system you've developed.
That's a good question. I mean, iron workers right now,
I mean, can some people speak out of the crowd to that question, high-skilled labor associated with welding, and being able to get away from that. Vern?
Yeah, it would be a great savings, because you have many more certifications that keep them up, going training behind it, all of them. But there'll always be somewhere you're gonna weld, but it is hard to find all the welders.
And I think it's somewhat of a dying breed. I mean,
It is.
Kids want to buy a computer, right?
Yeah.
They don't want to get out there and
But it's also a matter of testing as well, because with all those wells, there's a certain amount of testing that you have to do. Especially for whole system, and that way also you've got that additional safety factor. Get the testing done, sorry, they're not up into the, electrical spec as well.
It's very good.
It's not
But yeah, fuel welding is super expensive. The average cost of an iron worker that I send out to the field right now is $103 to $105. Very expensive field to weld.
The other thing I see here is storage mold. They can just, you can attach a precast, attach a wall, attach a curtain wall. Different contractors go down. They all see it. See when they bid, they pay out only to, it's one of
Yeah, back there, Matt?
Matt, Quinlan, JEI Structural. Can you touch on, are there any concerns, should you see, you discussed out-of-plane loading. Are there any concerns with seismic or loading in the plane?
You wanted a $10,000 for it, you got it. I'll give it to you back in the office. Yeah, you know, this is a question that I kind of worked with just recently, and looking at, you know, what can we do about lateral seismic loads, or just even loads that we get from a different plane of curtain wall tugging on, you know, part of the corner system. What can we do associated with that? I went to one of my friends and associates who serves on CEON, which is California Structural Engineer Association, and he actually lectures, and he actually contributes to part of the code in seismic. He's an expert in seismic design, and so that's what he does with his consulting business. I asked him, I said, you know, what can we do about this? Are we subject to the same types of things that the concrete embed channels are subject to? Or are we subject to the criteria that comes out of the steel design part of the code and the steel manual, where we can use slip critical connections? And he said, as long as you have steel to steel, it's no different than having a steel structure on the exterior side of your building. And so we would be able to design slip critical connections, which means that it's based upon friction in the bolt tension, resisting the lateral load. So that's answer number one. Answer number two is we have the possibility of being able to work in some connections if we need to stop movement and to take some of the lateral load. Answer number three would be, for this area, it's really sweet. We don't have to worry about seismic loads. Usually, we're in a seismic category A or B. We don't even really have to calculate seismic loads on the facade systems and be able to translate those into the anchor system. In seismic zone or seismic category C, then we have the possibility of being able to use friction clips per ASCE 7. There's a possibility there. And then after that, we have some additional work to be able to get into the seismic design for friction type of anchors.
Which we're currently looking into ideas with wooden roofs and bolts and stuff like that.
Yeah. All right, you get a $10,000
That was a setup.
Yeah, I think it was. Other questions? Thank you all so much for having me here tonight to speak and to present. I really appreciate it.